Okay, in this particular lecture, we're going to talk about two important properties of the Laplace transform. And that is what happens when you take the Laplace transform of a derivative and or an integral. So as we previously said, the Laplace transform's a method of solving ordinary differential equations and initial value problems. And the main thing that makes this very useful is that we can basically replace calculus and derivatives with algebraic operations when we take a transform. We can then solve in the Laplace domain, and then we can inverse transform back to the time domain. So this is particularly useful in solving complicated differential equations. So the first thing we have to understand is how to find the Laplace transform of a derivative. So that's what this section covers. So it's basically a very simple theorem. In this particular example, we're looking at first and second derivatives only, and then on the next slide, we'll look at a generalization for the nth derivative. So if you have the derivative of a function f, if you take the Laplace transform of that function f's derivative, basically that corresponds in the Laplace domain to multiplication of the transform by s and subtraction of the initial condition. In electrical engineering, we'll often refer to this as zero minus. It would be analogous to if you were solving a differential equation for a capacitor voltage and the capacitor had an initial condition on the voltage, then this would represent the initial condition of the voltage. L of f represents the Laplace transform of the function f, and s is a consequence of taking the first derivative. So this can be expanded for the second derivative. In the second derivative, we basically would have an s squared multiplying the transform of f, and then this initial condition f of 0 is multiplied by an s, and then we have an initial condition on the first derivative f prime. So a couple of comments. Notice that the order of derivative generates that number of initial conditions. So if we have a first order derivative, we must have one initial condition. If we have a second order derivative, we must have two initial conditions, one on the function at 0 and one on the function's derivative at 0. And so this continues in a pattern. So when we look at the general form of the nth derivative of the function f, the Laplace transform of that is s to the n times the Laplace transform of f, and then minus decreasing powers of s times initial conditions on the function, its first derivative, its second derivative, and so on until you reach the n minus 1 derivative. So oftentimes our initial conditions will all be 0, which makes for a very easy s to the n times the Laplace transform of f. But if we have initial conditions, they have to be included in this equation. And so if you're modeling, for example, the voltage in a circuit, then you would need initial conditions on the voltage 0, the voltage's first derivative at 0, and so on. The Laplace transform of the integral of a function is very similar. So because differentiation and integration are inverse operations, you can kind of logically say that multiplication and division are inverse operations. So we would expect, since differentiation results in multiplication of a transform by s, that integration would correspond to the division of the transform by s. And in fact it does. So if we have the integral of some function, and being a mathematics textbook, this is using the dummy variable tau. So if we have the integral of a function, and this is, notice, is an integral up to t, so that we would have a function of t come out of this integral. Basically, if we were to take the transform of f of t, we would get f of s, and then to account for the integration, we have 1 over s. Both the derivative and integral formulations can be proven using integration by parts. So now let's look at what happens if we have a differential equation and we want to use the Laplace transform to solve that. So in this example, we have this second order differential equation including a and b. It's inhomogeneous, so we have some r of t that in the physical problem would represent a driving force or an input that's applied to the system. the output will be y of t, and so the differential equation represents, in electrical engineering, it probably represents an RLC circuit with some input function r of t. We have an initial condition at t equals 0 of constant k naught, and we have an initial condition on the first derivative that's constant k1. So the first step in Laplace's equation is to set up the subsidiary equation. So this is going to be an algebraic equation for the transform, and we do that by applying the derivative formulas. So our first term, which is the second derivative of y, when we take the transform, essentially, let me go back. Let's look at the previous slide. So what we're really going to do is we're going to apply the principle of linearity, and we're going to take the Laplace transform term by term in this equation. So we're transforming the entire equation. So the first part of that is the second derivative of y, which when we apply the derivative formula, we get this expression. And then we have the first derivative of y, which generates this expression times the constant a. And then we have y itself, which when it's transformed just generates y as a function of s. And then r of s represents whatever the transform is of the function r of t. So now we collect like terms, meaning basically we're trying to solve our differential equation. So we're going to collect y. So keep in mind here, y of 0 and y prime of 0 are constants that are given. R of s is a given function. So what's unknown here is y of s. So that's what we're solving for. So if you collect like terms in y and move everything else to the other side of the equal sign, you get this equation right here. And then we can isolate y by dividing both sides by this polynomial. So when we do that, we get what's known as a transfer function. Let's go back a step. So in this case, y is going to be all of this stuff on the right hand side of the equal sign divided by our s squared plus as plus b. They're just basically putting a 1 there to have a discussion of a transfer function in general. So when you solve a homogeneous differential equation or a physical problem that doesn't have an input, your denominator is what's really going to determine the response of the system as far as kind of general grouping. So this is just an example of what you would do if you had a constant 1 here over this denominator. So what's being done here is they're completing the square so that you can get this into kind of a generalized expression. And then when you do that, okay, here's our solution for y of s. So basically you have this q, which is our function on the previous page, and I admit this is a very ridiculous way to represent this. So just going through the textbook's slides is, you know, I wouldn't, if I were lecturing live, I wouldn't do it this way because it's just confusing. Basically, you're just taking this 1 over what was on the left-hand side of that original equation, and then you're putting q here as just a way to represent, you know, what's going on. So first of all, if all of our initial conditions are equal to 0, then you get the output is equal to this function r times this function q, where q is output over input. And so q is representing a transfer function with no initial conditions. Now, the reason to talk about this is, let's suppose we have some kind of circuit. We'll say maybe it's a filter circuit. What Q gives you an idea of is it gives you an idea of how the circuit responds based on what physically comprises the circuit. So it's independent of input and output. It's only a function of what's physically there in the circuit. And so there's some usefulness in this, because once the transfer function is obtained, then you can find the output for a number of different inputs because you have the transfer function. And you can also determine what is it that is a response that's a natural response or a response due to physically what's in the circuit, and what part of the response is the driven response or the response based on what the input is. So Q does not depend on the input or the initial conditions, and that's what they're trying to get at with using this function Q. Okay, so once we have the function y as a function of s, what we're going to do in order to find the solution is take the inverse transform of y. Usually that's done with a partial fraction expansion, or it can be done with a computer-aided system, and it's fairly easy to do this in MATLAB. So I will definitely show you how to do this in MATLAB because I think that's pretty useful. Partial fraction expansion can also be done in MATLAB. It can be done by hand. Partial fraction expansion by hand is usually fairly straightforward. In MATLAB, it's not hard, but sometimes you have to manipulate what you get as an output into what you want in order to be able to take an inverse transform. So here's a very simple example of an initial value problem, and we'll go through the Laplace transform steps. So I have y, second derivative of y minus y is equal to t, and I have an initial condition on y at 0 and on y prime. So the first thing I do is take the Laplace transform of the entire equation. So the first term will give me s squared y minus sy at 0 minus y prime at 0. The second term just gives me the transform of y. The t ramp function transforms into 1 over s squared. So now we're going to follow the steps. So we will substitute for y at 0 and y prime of 0 with the constants 1 and 1 respectively. We'll collect like terms for y, and that'll give us this equation. Okay, given that equation, we now determine that our transfer function q is 1 over s squared minus 1, and that's going to associate with each term. Now you might ask, so here's what was on the right-hand side of the equation. Here's our function q, which is our 1 over s squared minus 1. So when we do that, we get s plus 1 over s squared minus 1, and then we get this term here. So the first thing we want to do is some algebraic simplification, noticing that this denominator factors into s minus 1, s plus 1. So we can write that as just 1 over s minus 1. And then we have this second term. So the second term is the term that comes from a partial fraction expansion. Getting from this point to this point requires that we take this term, do a partial fraction expansion, and get this result. Once we have it to this point, we're ready to take the inverse transform. We do that by looking up term by term on the table. So we have our first term, our second term, and our third term. Each one of these, now that we've expanded this using partial fraction expansion, is going to correspond directly to a term that we can look up on the table. So we'll have our e to the t, our hyperbolic sine of t, and our minus t, the ramp function. Now let me go back and talk a little bit physically about this function. If you look at the response, we have that e to the t, which represents exponential growth. And we also have a ramp function. So the solution of this is an unbounded or unstable kind of function. You kind of know that from the beginning, because you know that if you've got a ramp function driving a problem, that there's no bound on the input, so there won't be a bound on the output. You also know, as soon as you see this s squared minus 1 in the transfer function, and you realize that that has a positive real root, positive real roots always correspond physically to exponential growth. So in many ways, if this were a circuits class and you got this as a solution, I would tell you that your solution's unphysical, because you're not going to have unlimited exponential growth in an electrical engineering circuits problem. So you would need to go back and try and figure out if maybe your differential equation was wrong or you'd made some kind of error. So that's kind of a clue, if you have this kind of result, that you're probably getting an unphysical kind of result, at least in any problem that we would actually try to realistically model. All right, but the problem does illustrate our general approach, which is in the time domain or time space, we are given a problem That has to have initial conditions specified or we can't solve the problem. We then transform into the S domain or S space and we get this subsidiary equation, which, by the way, I have always referred to as a characteristic equation and probably will do so when lecturing in class. We then solve algebraically the subsidiary equation, and then we take the inverse transform to get back to the time domain space. So even though it seems like we're adding extra steps, if we were to try to solve this differential equation as is, that would be a difficult differential equation to solve. So it actually turns out to be easier in this case to solve that in the Laplace domain. So just to summarize, there are some advantages in using the Laplace method to solve differential equations. First of all, as we just illustrated, we can have an inhomogeneous differential equation and we don't have to do a two-step solution. The initial values are automatically taken care of, so we don't have to do a particular solution. And we can have fairly complicated inputs that can be handled pretty efficiently and effectively. So the Laplace transform is a good way to solve different